Okay, so we just finished talking about CRISPR, which was our first favorite Nobel Prize. We're going to talk about our second one, a great achievement for American science.
This was all America.
This is us.
Yeah.
America. And which is the sort of LIGO. And again, we're tying it from the AI story that just came out this year to the history of this project and how AI is making this initial tool and kind of area of research even better. So the headline on this LIGO story, new algorithm hushes unwanted noise in LIGO, may lead to more black hole discoveries. So this is from researchers at Caltech, and their idea was we want to make it easier for LIGO to find black holes with eccentric or oblong orbits, as well as catch mergers earlier in the coalescing process.
Yes.
They published their paper in Science, which is this AI kind of context. But we've talked about LIGO on the podcast before, and I remember you talking about how this is sort of this like long tail of this initial contribution of what Einstein predicted 100 years ago.
100 years ago, yeah.
And so we're going to do the same thing again, which is kind of look at this story of the scientific curiosity journey from that initial prediction now to how all these new AI things are actually making LIGO better.
Yeah. It's kind of crazy. 100 years ago, actually more than 100 years ago, so 1915, Einstein publishes his general relativity, which is a new way of thinking about gravitation, not as a force in the sense of Newton, where there's a force between two bodies, but actually as a disturbance in the actual fabric of space and time, where now you have this unified quantity called space and time, which he had sort of already unified in 1905 with special relativity, but special relativity dealt with inertial reference frames, which means a reference frame here, let's say us sitting stationary, and then a frame of someone in a car that's moving in a straight line with constant velocity. The idea is any experiment that he does in there is the same as any experiment that we do stationary. This is kind of, he's taking Galilean relativity from Galileo's time and taking it very, very seriously, right? And he's combining that with the fact that the speed of light is constant to get special relativity. All these consequences about how time is really relative, space is really relative, and there's this metric that is a combination of the two that is the thing that is invariant. Okay, so now we get special relativity. General relativity is where he generalizes it to say, what about accelerating reference frames? What if that train was not moving in a constant velocity, but was moving around, was turning, was speeding up or slowing down? How would that affect these calculations that I've been making? And he comes up with general relativity, which is this idea that gravity and acceleration, gravity and this change in space and time are actually the same thing. We don't have to get into the whole details, but at the end of the day, it created this sort of nice mathematical framework for how we identify and understand space and time in a very nitty-gritty, precise way.
Which impacts us, every day.
Every day. And I mean, GPS, for example, is impacted by general relativity. The fact that GPS satellites are so far up means that they have a smaller gravitational field due to the Earth compared to us down here, which means that their clocks actually run a little bit faster than ours do.
Right.
You would think because of special relativity that their clocks would run slower.
Yes.
Right? Because they're moving so fast.
Yes.
But actually the general relativistic effect is something like 4 times the effect from special relativity. So special relativity, the fact that they're moving so fast means that the clock is slowing down. But the fact that they're in such a smaller gravitational environment, right, where the gravity is so less, means that they're actually moving faster.
Which is why there's a correlation. That's like these things matter. Like
and actually like measuring that and accounting for that is essential to how GPS works.
How we get
because
precision.
At the end of because at the end, like GPS can like localize me to within a few meters of where I actually am, right? That few meters, if you think about it, the way they actually do it is from the light traveling between us and the satellite, and the time delay between us and several different satellites, right? And then triangulating from those several different satellites to where we are. Well, in order to actually measure that time difference, you need to have extremely precise clocks on that GPS satellite.
Yes.
That precise clock is going to be so precise that it is going to feel these relativistic effects. And so you need to have an active mechanism that accounts for the fact that that clock is going faster than this clock by exactly the amount that Einstein's field equations say that they will go faster by. And then you do the math, and then you like, oh, you're here, you know, and you need to go over there, and so on and so forth.
That's actually a really good
example. So it's very much like involved in.
Right. It's a good example of how GR relates to a very everyday use case that everyone can understand.
Everyone, yeah. Everyone's used GPS.
Yes.
Okay, so now we're getting to the fact that Einstein publishes these field equations. People start trying to find solutions to the field equations, okay? Which means to say, the field equations give us a way to understand what matter does to space and what space does to matter. The great saying by John Wheeler, who we'll get to later on, is that space tells matter how to move and matter tells space how to curve. Okay? That's effectively what Einstein's field equations are. They're a way for us to mathematically describe the stretching and turning of space-time. Okay? So space-time becomes this sort of like field in some sense. Okay, it's like everywhere, and it's got a way to stretch and stuff. And one can imagine people start asking, can I make waves in this field of
right?
In this sort of field of space-time? You can imagine, right? Like if I've got ropes or if I've got a rubber band, right? I can create waves in my rubber band. If I have a bunch of rubber bands lined up together and I stretch one and then that sort of propagates on the rest, you can create these waves in rubber bands. And if space-time is this sort of elastic thing, then I should be able to create waves in space-time.
My initial thought on that is you must need an immense amount of energy.
Yes. An insane amount of energy.
In order to disrupt the fabric of space-time.
Yeah. I mean, and you're exactly right. You do need an insane amount of energy to disrupt the fabric of space and time. But before we even try to think about what could cause waves in space and time, you got to first show that the Einstein field equations admit a solution that looks like the wave equation. Okay? The wave equation is something that's been around for hundreds of years, and it's very well defined, sines and cosines traveling. The wave equation is a very simple second-order differential equation that's basically saying that the amount of curvature that I have in space tells me how much acceleration I have in time. And that's basically how the wave equation works, right? There's a second derivative in space, there's a second derivative in time, and they're related by the velocity of propagation. So Einstein sets out to see if this works in his equations of special relativity, in his field equations. So at this point, it's in the 1930s.
Yep.
Einstein's already at Princeton, New Jersey. He's already at the Institute for Advanced Study. At this point, I don't think the institute had actually been made, and so he had an office in Frist Campus Center, which used to be the old physics building and the math building on campus. So
spent a lot of 2 a.m. nights.
With the late meal.
Remember that?
That
late meal
was
classic.
So he's sitting there, and he tries to find a solution to the wave equation in his field equations. He does the math. And he actually comes up with the fact that what he notices are these things called singularities, which he can't quite get rid of when he's trying to do this analysis. And so he writes a paper saying that the wave equations, the field equations do not admit wave solutions. Okay, he writes this up and he sends it over to the Physical Review. Okay, the Physical Review at this point was. The editor was John Tate, and he is kind of a stickler for the peer review process. At this point, Einstein had already sent in a bunch of papers to the peer review. There was the very famous EPR paper, Einstein-Podolsky-Rosen, which is the one that was talking about local variables solving quantum mechanics. Mm-hmm. He was saying that, this whole quantum stuff is weird. Maybe there's some hidden variable that explains quantum mechanics. That was the famous EPR paper. There was also the Einstein-Rosen bridge paper that he had published in the peer physical review. So he's had a pretty good relationship with the physical review. Yes. So he sends this one in, and he says that my equations do not allow for wave-like solutions. John Tate sends it over to his buddy H.P. Robertson, who's also in the Princeton physics department. So Einstein sends it to John Tate. John Tate sends it back to Princeton. And Robertson finds an error in the paper, okay? He finds that the singularities that Einstein is so worried about and the reason why he thinks that wave equations won't exist are actually just coordinate singularities. They're not actually real physical singularities. Coordinate singularities are something like, trying to find the longitude of the North Pole, something like that. It's an artifact of our version of how we're keeping track of latitude and longitude, right? But the North Pole could be anywhere, right? It's just we like the North Pole at the top because that's how it's spinning. But you can easily imagine a coordinate system where the North Pole and the South Pole are on the opposite sides of the equator, and we just have really convoluted equations of mechanics for how physics on the Earth works, right? But at the end of the day, it's a choice that we've made as humans on where to put the zero of our coordinate system, right? It's an artifact of the coordinate system. So Robertson actually looks at Einstein's paper and he's like, actually, these singularities are coordinate singularities. They're not physical singularities. So he writes back to Tate. Tate then pushes back on Einstein and he's like, hey, I got these peer reviews. I was wondering if very nicely the letters are still there.
Not like reviewer number one.
No, not like reviewer number one from the Mars paper, where it's like you need to this needs to get rejected. It's like this is Einstein we're talking about. So obviously you have to be like, they have these comments. Can you take a look? And Einstein is just livid. Okay, he's like, I can't believe you showed my paper to someone without my consent. Given this, I'm just going to publish somewhere else. He retracts his paper.
The goat.
He never publishes in Physical Review again. And John Tate goes down as the guy who editorialized Einstein. But he was true, a man true to his word. He was like, I don't care if you're Einstein or God. You're going to go through the same peer review. And hey, if Robertson, who's a great mathematical physicist in his own right, says something is wrong, maybe you need to pay attention, right?
Seems
reasonable. Einstein retracts his paper. He gets word from his assistant elsewhere about Robertson, because Robertson goes to his assistant and is like, you guys are having trouble with these singularities. Like, there's one way that you can just do this and then blah, blah, blah. And then the math trick works out. And so Einstein gets word from his assistant that, there's a way to counteract it. He goes back to the drawing board. And Einstein, true to his physics side, right? He sets aside his ego and he's like, okay, that was bad. and he corrects his paper. And he publishes it in a Philadelphia journal. I think of the Benjamin Franklin Society or something, some random journal. Not the Physical Review. Right. And it's a totally new paper.
Okay.
And it's a new paper that admits that gravitational waves can, in fact, be allowed in the space-time of Einstein's field equations.
Yes.
It's so funny, right? Because it's like this guy, he you should have just read the peer review. Right. He could have just read the peer review and but he had to go through all this.
He chose violence.
And at the end of the day, he even admitted to himself that he was wrong and corrected his paper, but he never went back to the peer review.
That's a level of petty I aspire to be.
Yeah. It's like, I know I'm wrong, but how dare you? That's Einstein, dude. You don't. Yeah. Anyways, he never published in the peer review, the Physical Review ever again. But that paper sort of established this idea that we can have gravitational waves.
You can have waves in this system of space-time where space-time is this fabric.
Yeah, that governs the dynamics of all things. Okay? So all right, fine. Now we've got a paper that says gravitational waves do exist.
Right.
Okay? Just like electromagnetic waves.
Yes.
Okay. And just like electromagnetic waves, in order to create gravitational waves, you need accelerating bodies. So you can't have a thing that's just moving at constant velocity.
Because it's not going to disturb.
Because it's not going to disturb space in the way that it propagates out.
Yes.
Okay? It's going to create a disturbance, but that disturbance is just going to like sort of be local to it.
Yes.
Okay? And you're not going to get this like radiating effect.
It's like if you're in a boat and you're stationary, you don't create a wake. But if you're moving,
but in a boat, even a moving boat creates. This is a big.
Okay.
This is a fine detail. A boat that's moving at constant velocity is still going to create waves.
Yes, that's fair. That's fair.
A charged particle that moves at a constant velocity will not create
waves.
a light wave.
Interesting.
Light is only created from accelerating particles. So something that's moving in a circle means that it's changing velocity. That is going to create a radiating effect. Something that's speeding up or slowing down is going to create a radiating effect. But something that is moving at a constant velocity is not. There's actually a very simple argument for why this is the case. It's one of my favorite arguments about from Einstein's special relativity. Okay, so suppose not, right? We're going to do this by a proof of contradiction. Suppose not. Suppose that a charged particle that moves at a constant speed does create light. What if I were to boost myself into a reference frame that I'm moving with the charged particle at a constant speed? In my reference frame, that charged particle is stationary.
Yes.
So I'm not going to see any light. But now there's a contradiction.
Yeah, right. Immediately. Got it.
Immediately there's a contradiction because a stationary observer observed light, but me moving with this particle does not observe light. It would be something if the stationary observer observed a particle with some light and I observed it at a different energy, right? Yes. Maybe it was like boosted in ultraviolet or down in infrared or something like that. But the fact that I observed no light is unphysical.
Yes.
Because both me and the stationary observer should observe the same physics.
Yes.
Right?
Yes.
So it's a consequence of relativity that constant velocity motion does not radiate.
Okay.
The same thing happens with gravity, right? Suppose there's a gravitational object that's moving at a constant velocity. If I boost myself into that reference frame, that object is now stationary and I shouldn't observe any gravitational waves. Well, if I don't observe any gravitational waves in my frame of reference with the body, then a stationary observer should also not observe gravitational waves. On the other hand, if it's accelerating, if it's moving, if it's accelerating and it's speeding up or it's slowing down, then no matter what inertial frame I choose, it's also going to be either speeding up or slowing down. So I am going to observe some form of gravitational radiation, or in the case of charged particles, some form of electrical radiation, light. You know, that's kind of interesting.
No, that's a great.
It's such a great, like, simple argument you can make using just the symmetries of physics. So, anyways, we need something that's accelerating. Okay. So for the longest time, gravitational radiation was just this thing that, you know, it's hypothesized, but even Einstein said you're never going to find it.
Yeah.
Never. Because you can do a back of the envelope calculation about how much stuff would stretch and squeeze by.
Right.
And it's on the factor of like 10 to the minus 20.
Meaning like the actual fabric that would be measurable by us would be so...
Any length would be corrected by 10 to the minus 20. Right? Like if you take a meter stick, an atom is 10 to the minus 10 of that meter stick. Right? So it's an atom of an atom. It's just like, even Einstein's like, okay. Right. Like this is a cool, like, you know, theoretical exercise. But
so the point being that his view was like, we won't be able to get to a level of experimental verification because of the scope is just so outside. Like it was an engineering problem for detection, and that we weren't.
But the engineering problem required physics that was like stupid. Right?
Yeah.
You know what I mean? And he was just like, it's like a cool thing.
Yeah.
But it's a cool thing.
Yes.
Okay. 1970s actually is when we first got a confirmation that gravitational waves exist.
Okay.
It was by Taylor and Holtz. Actually, one of their plaques is on the Princeton University physics thing because he won the Nobel Prize for it. I think he was a postdoc at the time at Princeton, and or maybe a PhD student. So they use the Arecibo radio telescope.
Yep.
Have you seen this
Yes,
thing in
yes,
Puerto Rico?
yes.
It's a giant radio telescope
Yes.
that's like
In the-
in a bowl created by the geography of the mountain.
Wasn't it recently kind of had like a hurricane came through or something, had a little damage
Yes,
to
it did.
and then they had to
they had to fix it and
Yes.
everything. But it's a bowl created by the Earth,
Right.
that we then put concrete over, and then it basically just scans the sky with the Earth.
Yes.
And tries to find radio sources. So they were trying to look for pulsars at the time with that radio source, and what they found was a pulsar. And they were very happy because back in the day, like pulsars were very new, so they found a new pulsar. But this was a very weird pulsar. Okay, it was a pulsar that had a cycle of 60 milliseconds. So 17 times a second it would. 17 times a second it would like go down.
Yes.
And a pulsar is basically a neutron star that kind of acts like a lighthouse. It's got these strong magnetic fields, so it's got these jets of radio light that are coming out, and it's a lighthouse in the sense that as it rotates, right?
Yes.
The part of the beam, the radio beam, is gonna just like go through the Earth.
Yes.
Every 60 milliseconds.
Yes.
Right.
Which is quite fast.
It's quite fast, and it's a really precise clock. Okay. It's these pulsars are some of the most precise clocks ever made in the universe. Right? Because it's really hard to slow down a neutron star that's the size of several suns, that just because of the conservation of angular momentum, it's just going to keep going. Okay? So most pulsars, they're very reliable. They'll just be like clockwork. This pulsar was different. Okay? Because this pulsar, every once in a while, it would the pulses would arrive 3 seconds too late or 3 seconds too early. Remember, it's going at 60 milliseconds, but you can plot the trajectory of how their delay is.
Yes.
And that delay was happening 3 seconds too late or 3 seconds too early. And what they figured was this pulsar is actually rotating with another neutron star. That other second neutron star is also a pulsar, but we're not seeing it because the lighthouse isn't crossing our line of sight.
Yes.
So it's maybe doing one of these and we're missing that lighthouse
going up,
effect.
down instead of...
But this one is coming right at us, and it's revolving in this binary pulsar system.
Got it.
Okay? This became a really nice test bed for general relativity. Because now all of a sudden you had rotating objects that were massive, that were accelerating, right?
Yes.
Because they're revolving around each other, which means they're constantly correcting their motion because of the gravity between them, which means if they're close to each other, right, 3 seconds in light distance, like the moon is about 1.5 seconds away. So this is, imagine like it's the Earth and like another two moons away.
Yes.
Two stars that are like the size of the sun and more,
yes,
that are revolving around each other, right?
So the point is they're quite close.
They're quite close.
So their gravitational impact, their gravity independently is going to have a high impact on each other because of proximity.
Exactly.
Yeah.
Which means that, according to Einstein's GR, these should be radiating gravitational waves. If they're radiating gravitational waves, then they should be losing energy, because it takes energy to deform space and time.
Yes.
And if they're losing energy, they should be falling into each other, and they should be rotating faster. So you can do all of the math.
I was going to say you can do the math.
You can do the math, and you can figure out, according to GR, how fast should that decay be, right? Of their total energy.
Yes.
And it's a beautiful plot that they have in their paper, where it shows a line that shows the theoretical prediction, and then it shows dots
with
of the experiment, and the dots are lining up exactly to Einstein's GR.
Which means the math in the GR paper is now, which was theoretical at the time, there's now an experimental observation that was verifiable to what the underlying sort of statement of work is around GR itself.
Yeah, exactly. And it's like where could this energy be going? It has to be going in the gravitational waves, which is what's predicted by this equation, and the equation also predicts exactly the decay, and that's exactly what we see. And now we've been watching this pulsar for the past 40 years now,
which makes sense.
And it just continues down.
It's like the perfect experiment in the sky. For any number of different types of observational, you know, research. This being just one.
Yeah, and they won the Nobel Prize in 1993 in physics for this discovery. It was a very big one, right? It established the reality, the experimental reality of gravitational waves. Okay. Now,
I just want to make a note that what's interesting is it required no specialized measurement equipment.
No.
At the time, it was just what we already had: radio telescope.
Yeah, it was just a radio telescope
and
Arecibo. Yeah, Arecibo and math, right? And so this established at least the existence of gravitational waves, of the fact that space and time undulate in this wave-like manner, and it carries energy, the same exact amount of energy that Einstein's equations predict. Okay, now it's something to go from these things exist to let's actively try and sense them.
Right.
Okay. Right. Because that's what Einstein was going at. He was like, "This is going to be impossible to sense these things."
This was an indirect confirmation.
It's an indirect observation.
But it was not a direct observation.
No, it's not like, oh, that was a good I just saw one.
Yeah.
Right? It's just like, oh, this thing is just putting it out into the sky, and we're seeing it because it's losing energy. Right? So that's the indirect observation. By the conservation of energy, that energy has to go somewhere. Where does it go? Into these gravitational waves.
Yep.
Okay. So now we're getting to so this is in the 1970s they find this thing. Also in the 1970s, people start thinking about how do we actually make a direct detection of gravitational waves. So that's where we start getting into people like Feynman. Actually, Feynman starts. He gave this talk about sort of a thought experiment of how to actually detect gravitational waves, and he showed that if you had like a sort of rod attached to springs and stuff, and if a gravitational wave of insanely high capacity went through, then the rod would actually undulate because the springs would be attached to that space and time. So this thing would like move, and then part of the energy of the gravitational wave would actually go into the spring, and then if you measured the spring, you could actually measure the gravitational wave. So he showed that mathematics of like something like this
like
would
a
actually work.
System that could do the direct observation, and what the structure of that system would be and why it can work.
Exactly. And so given that sort of theoretical work of showing that a system like that would work, this guy Joseph Weber from the University of Maryland in the 1960s and 70s, he created a gravitational wave detector, which was sort of something that he could fit inside a laboratory. And he said that he found some. Now we know that he probably didn't, because people couldn't replicate it as his experiment, and science is all about replication, right? And probably he didn't find any. And it sort of marred the field because, you've got this guy who's saying, I found him, but he didn't. And he was an honest scientist, but, even honest scientists can get sort of hung up and not see the sources of their errors, right? So it was kind of lacking, let's say, the field. Okay, so this is where the two heroes of our story come in, Kip Thorne and Rainer Weiss. Okay, and to really understand where they come in the 1970s and 80s, we got to go back to their roots. Okay, Kip Thorne gets his PhD at Princeton under John Wheeler. Okay, John Wheeler is a seminal figure in the field of physics. Okay, he's kind of like, I would say, the American Arnold Sommerfeld. Remember Sommerfeld that we talked about?
Yes.
Sommerfeld being this guy who tutored amazing physicists in their own right, but never won the Nobel Prize himself. John Wheeler is one of those guys. Okay, he tutored Kip Thorne, won the Nobel Prize. He tutored Richard Feynman, also got his PhD under John Wheeler. He tutored Hugh Everett, who is the guy behind the many worlds interpretation of quantum mechanics, this idea of multiverses and all the, Marvel stuff. He also tutored Jacob Bekenstein, which is a guy who did seminal contributions to black hole thermodynamics, the idea of like entropy in black holes and information in black holes. He sort of revamped, he made general relativity cool again after the war.
Yeah, okay.
Yeah, because general relativity was sort of this field that was not cool. Okay, it wasn't something that you could do direct detection on. Einstein had sort of closed the book, by finding the Einstein field equations, and then people thought it was sort of just it's just bookwork at that point of like trying to find new directions with GR.
Is it similar to how when people say string theory is cool on paper, but we can't do anything experimentally to really see the things that are being argued? So like it's a parallel.
It's kind of parallel. GR I wouldn't compare to string theory, obviously, because GR actually has insane experimental. Even back then.
Okay, fair.
Right, even
fair.
Like Mercury's orbit was explained by GR.
Fair.
One had done the detection of bending of light around a solar eclipse. That was Arthur Eddington. So GR had its confirmation.
So you're saying string theory is trash? I'm kidding.
Yeah.
I'm kidding.
Well, okay. Actually, in a speaking of string theory actually started with John Wheeler. John Wheeler came up with this idea of the S matrix, which was. I don't understand much about it, but it's some way of like defining a new way of dealing with quantum mechanics that had to do with combining gravity and quantum mechanics. S matrix was then taken by Werner Heisenberg and developed into a theory, and then that sort of formed into string theory later on. So John Wheeler is even, in fact, responsible for
that whole wing,
the genesis, the very, very embryonic genesis of string theory. He did a lot of really crazy stuff, dude. He did S-matrix theory. He coined the term wormhole. He did the one electron universe. I don't know if you've heard about that, where it's like every electron is just one electron in many different... Like, people love trying to go into, like, the science fiction of this kind of stuff. He popularized the term black hole. He also actually was one of the first people to foray into quantum gravity, of trying to combine quantum mechanics with gravity.
Yes.
So this incredible physicist sort of became the, this godhead status at Princeton physics. Attracted the talent. Created talent with Kip Thorne and with Feynman, but he never himself won the Nobel Prize.
He was the prince who never became king.
Yeah, but I mean, to those who know physics, like John Wheeler is a very big deal, right? He was one of the few people who he defended Freeman Dyson when Freeman Dyson was going up against Oppenheimer. It was like, he's one of the few guys that can like go against the bigwigs, even go up against Einstein and be like, nah, that doesn't make sense. And Einstein would actually listen instead of being like, I'm never going to publish here. And Kip Thorne was Wheeler's PhD student.
Yep. And
Wheeler sort of started this idea of revamping general relativity. Okay. Kip Thorne grew into that. They wrote textbooks together, and Wheeler was the sort of theoretical part of the wing, and then there was this experimental part that was Robert Dicke. Okay, Robert Dicke is another one of these guys, great Princeton greats. He's responsible for the invention of the lock-in amplifier, which is an electrical way of finding small electrical signals that are of some characteristic frequency in a bastion of noise. He also was the discoverer of the cosmic microwave background. Okay, the CMB, the radiation from the Big Bang.
Yes.
He was one of these first sort of applying general relativity to cosmology problems. And him and his student Wilkinson and Peebles published the paper right after the experimental discovery. They were actually planning to make a dish to observe the cosmic microwave background. And then, meanwhile, unbeknownst to them, Penzias and Wilson were neighboring in Bell Labs, which is right down the street from Princeton. They were stuck with a microwave antenna. They're trying to do research with microwave antenna, and they keep getting this noise.
Yep.
And they're like, what the hell is this noise? And they're trying to find where the noise is coming from. One of them actually like crawled in and started like scraping the pigeon poop that was in the antenna, because they're like, I don't know, maybe it's the pigeon poop, and they're like scraping. They got rid of the pigeon poop. The noise was still there, and they're like, dude, what is this noise that we're getting? And they called up Robert Dicke, and they're like, we're getting this noise. Like, you guys are physicists at Princeton, and Dickey's like, he hangs up the phone and he tells his collaborators, "Boys, I think we got scoop." Because they're trying to make a thing, and these guys have done it. Penzias and Wilson immediately recognize what it is. They immediately publish. Dickey, Peebles, and Wilkinson published their paper on the CMB, the theoretical background, right after theirs. So you can see when they published, actually, it's like back to back in the same issue of the journal they're publishing, right? And Penzias and Wilson go on to win the Nobel Prize for the discovery. It really should have been a three-person with Dickey. But actually, years later, I think in the last 2 or 3 years, Jim Peebles, who was the guy who published the theoretical paper, he actually won the Nobel Prize. And it was kind of a validation. It was kind of a posthumous Nobel Prize for Robert Dickey, who had already died. But it was kind of cool that that collaboration finally won the Nobel.
It got recognition.
Yeah, it got recognition. Peebles won it for all of the other stuff that he did with cosmology later on. He actually showed that, the CMB should look like this, with this bumpy, wavy nature when you look at the power spectrum. And then when people did the power spectrum, they found the bumpy, wavy nature. Wilkinson, who was the other guy who did the paper with them, the WMAP satellite, which is the Wilkinson anisotropy probe, that was sent into space to actually capture the cosmic microwave background in excruciating detail. That was named after Wilkinson. So, they got their credit in their own right, but it's unfortunate that Dickey didn't get his recognition with the Nobel Prize. But one of Dickey's postdocs was Rainer Weiss. And Rainer Weiss still to this day says that, one of his biggest influences in terms of physical thinking was Robert Dickey at Princeton. There's a beautiful photo of Kip Thorne and Robert Dickey standing right next to a plaque that commemorates... Sorry, there's a beautiful photo of Kip Thorne and Rainer Weiss, the 2 Nobel Prizes that were awarded for LIGO. They're standing next to the plaque that commemorates Robert Dickey at Frisk Campus Center, right? There was a big celebration of his work, and both of them were in attendance, along with Wilkinson, who was in attendance. So, it's this big tradition that sort of started at Princeton of let's take GR seriously.
Yeah.
Okay. They move on to their different things. Kip Thorne goes to Caltech. Rainer Weiss goes to MIT. And they start thinking more earnestly about gravitational research in the experimental domain. Okay. And they're like, can we actually do this? Can we actually...
The thing that Einstein said we
say
couldn't
that
do.
Einstein couldn't do, can we actually do this? Okay. Rainer Weiss starts thinking about it. He's more on the experimentalist side, so he's from Dickey's group, right? So he's trying to actually think about the experiment. And he comes up with this idea of the interferometer, okay? Which is really what LIGO's design is today. The idea is you've got an L-shaped instrument where I have light moving in this direction and light moving perpendicular. It's the same setup that Michelson-Morley used back in the late 1800s to show that light was moving in the same speed in both directions, regardless of an ether and all this other stuff. That same thing, what if we just made it big? Okay? What Rainer Weiss's main contribution was with that paper in the 1970s and 80s was to figure out what are the types of noise that I'm going to run into when I make an instrument of this scale and I want to measure something this precisely. Okay? And he came up with a list of all of the noise sources that they're going to have to deal with. There's going to be seismic noise, earthquakes. Even an earthquake that's on the other side of the world is going to create low frequency vibrations on the earth.
At the level that we're trying to measure.
And that's going to create stuff. The waves from the ocean, that's going to create noise. Cars and trucks, people walking by, that's going to create noise.
Elephants in the Sahara.
Yeah. like all the stuff that you could think of. He created a list of all the stuff that we would have to come up with. And at the end, he had something called quantum noise.
Okay.
Which is literally the Heisenberg uncertainty principle.
Yes.
Okay?
Yes.
It's like there's noise that we're not going to get rid of ever.
Yes.
Because that's just how it is.
Yes.
And we'll get back to that later because the AI story actually ties into that. So he made a list of all of these noise sources, and he came up with sort of the ways in which we can make this happen. Kip Thorne, on the other hand, he starts doing theoretical calculations of what are the sources in astronomy that could create these gravitational waves, right? That we would be able to see. Right. How often would these go off? Right. Given our assumptions about the universe. Right. And theoretically, is it possible, like that Heisenberg uncertainty limit, what is that limit? Right? Mm-hmm. Are we hopeless? Mm-hmm. Or is the Heisenberg uncertainty limit just below the sensitivity that we need to actually find these things? Right. Okay? So you've got these two. Rainer Weiss is spearheading the approach from the experimental side, and Kip Thorne is spearheading the approach from the theoretical side. Yes. Okay? They think that, maybe this could actually work. Okay? Right. They're like,
just so crazy.
They're like, maybe this could actually work.
The audacity.
Yeah, dude. And in the 70s, they decide to pitch it to the NSF. Mm-hmm. Okay,
National Science Foundation.
That's the National Science Foundation. They pitch it to the NSF, and the NSF is like, "This is
We have this amount of money.
Yeah, we have this amount of money, and what you're saying is something that Einstein said wouldn't work." So they're like, "All right, we're going to give you a little bit of funding. Why don't you try to get down to these sources of error? We're going to give you enough funding where you're not going to find gravitational waves, but you can at least start making a prototype to figure out if you can mitigate these sources of error."
Yeah, right.
Before we even get down to that 10 to the minus 20, let's get down to 10 to the minus 10. Mm-hmm. All right, where it's like, can you even theoretically and experimentally make such a instrument?
Yes.
Okay. So they start going into it. Caltech gets a telescope that's about 90 meters, which is pretty big.
Yeah.
Even then, MIT also gets an instrument, and they start experimenting with this kind of stuff, and it seems promising. It seems like they're actually working. So then Kip Thorne recruits Ron Draver, who's from Scotland, who had also worked on the early parts of this gravitational wave research. And he gets them together, and he's like, all right, we're going to pitch this thing. This is going to be big. It's going to be a big deal. All right, boys, we ready? So they start doing it. Upper management has turmoil. Personal reasons. Ron Draver doesn't get along with this guy Voigt, who's also part of the experimental collaboration. They just really don't get along.
You hate to see it.
You hate to see it, but the two of them are like, I'm out. So now Kip Thorne and Rainer Weiss are just like, okay.
Okay, it's just us again.
So it's just us again. NSF halts funding because they're like, you guys are like headless chickens. You have no idea what's going on. We're going to halt funding, and we're going to, if you guys come up with a strategy that actually makes sense and that isn't petty, then maybe we can talk. So that's when Kip Thorne invites Barry Barish, who was at Caltech. Mm-hmm. Okay, Barry Barish is, in 1994, he's brought on as the new director of the project. And Barry Barish is the reason why producers get the Best Picture award in the Oscars. Okay? The Oscars give the Best Picture award not to the directors or the writers. It goes to the producer. Okay. It's the guy who's putting it all together. Yeah. Barry Barish is that guy.
This is so random.
It's so random, but he's really he's an experimental physicist who does particle physics research. Okay. He was involved with the superconducting super collider, which had failed in Texas.
Yes.
So he had already learned his lessons there. Yeah. He knew how to deal with people.
Yes.
He knew how to figure out what he wanted. He knew how to talk to people to get what he wanted, and he knew how to get people on board.
He was the politician of the group.
He was the guy. Yeah, he was the guy who saw the big picture.
Yes.
And he's the guy who, when he was brought on, he transformed LIGO from a 40-man operation to this thousands of people. That is what is required to make that detection.
He became the wartime CEO.
Dude, and actually you say that, but somebody actually said to him, when they were advertising who Barry Barish is, at the time, the war in Iraq wasn't very popular.
Yes.
And they said, if Barry Barish was in charge of the war in Iraq, it would have been over by now. That's how they advertise him. He really was the wartime CEO.
Yeah.
He was the guy who was like, okay, we're gonna build this thing.
Yes.
We're gonna require 2 detectors.
Right.
We're gonna have one in Hanford,
yes,
in Washington State.
Yes.
This is actually the original site where we enriched plutonium for the Manhattan Project. Now it's being used for this. There's gonna be another one in Livingston, Louisiana.
Yes.
Okay. We're gonna build them 2. And he really started this collaboration, and it started taking a life of its own.
Yes.
And even Kip Thorne and Rainer Weiss were like, thank God for Barry Barish, you know, because he just full steam ahead.
Yep.
Like, we're gonna build this thing. I'm not gonna have another failure.
Yes.
Like the SSC on
Yes.
my hands.
Yes.
You know, and he all credit to him. You know, he created that collaboration that built this.
Every project always needs the operations guy.
Yeah.
It's funny. My dad works in stage 1 drug discovery, and he was over in Scotland, and there was a researcher at one of the Scotland universities that had a really interesting fundamental discovery. He went to go to VCs to say, hey, give me millions of dollars to make this a thing. And they were like, okay, great. And he wanted to be CEO. And they were like, we need a Barry Barish.
Mm-hmm.
We don't need a you. And my dad came in as that operations person who like understands the fundamentals.
Yes.
But understands the way in which the business world and all these things that are not about the science necessarily.
Yeah.
Do matter a lot.
Exactly.
When you're talking about these huge, large-scale projects.
Yeah. When you're talking about that, this is something that requires something beyond like knowing how the Einstein field equations work.
Right.
Which obviously Barry Barish does. He's a trained physicist.
Right.
But his real expertise is in this ability to manage 1,000 people towards one goal.
Which is not trivial.
It's not trivial, no. And this is the guy who did it, right?
So
and he, so he started construction.
Yes.
He got the money from NSF.
Yes.
He convinced NSF, this is going to work, guys. Yes. He got the money from NSF. It took 5 years to build the buildings in Livingston and Hanford in Washington and Louisiana, where, you've got these 3-kilometer long tunnels, right? And the tunnels are so long, they have to be kept completely straight that they're accounting for the curvature of of the earth, right? Where they have to actually go under a little bit and then get over, right?
Yes.
In the entire tunnel, you got to create a vacuum that's better than outer space in the entire 3-kilometer tunnel. And it's like the stupid stuff was actually hard, like creating a tunnel that's better than anything we've ever had.
Yes.
Right? All of the stuff was completely brand new.
Right.
You had to create the best mirror of all time to have these laser interferometers where the laser is going down both and then bouncing back. That mirror needs to be near perfect. And it is near perfect. It's near perfect glass. It's the best mirror that we've ever made. This mirror, if you left it ringing, right? Not that you would want to do this, but like if you like rang it and had it like vibrate, that thing would vibrate for 100 million times before actually stopping. Because there's nowhere for the energy to go in this vacuum.
Self-propagating.
Yeah, so it just stays within itself and becomes this like perfect spring pendulum thing that just vibrates, right? So you've got to create all of these new technologies, right?
Just to create the environment. And finally, in like 2001, you had LIGO in its first iteration. This is when the technology is there to find, if you're lucky, gravitational waves. And this was just a proof of concept to say that, okay, we've reached this far where we've reached the sensitivity level where if we get really lucky and there's like some massive merger that's like right next to us in the galactic neighborhood, we're going to find it. They didn't find anything. But that's science, right? The probability was very low. They solved a lot of the engineering problems, and this was the crawl, walk, run approach, and we're like in between the crawl and walk stage.
Yeah, they were in the walk stage at this point.
Got it.
Okay? And then they upgraded LIGO to this LIGO 2.0, to this higher sensitivity. And this is right around the 2010s. Okay? They're upgrading. And this is now the run. Now we're getting to a point where it is likely that we will catch gravitational waves.
If it were to pass the Earth, we are now able to detect it at a sufficiently small level that it will detect it if it is there.
That's right. Yeah. And so then comes the detection. Okay? This is September 14th, 2015. God, it's at 4:50 a.m. Louisiana time. The LIGO computers at both Louisiana, and Hanford detect something. Okay? They detect something, and they've got an automated email system that sends it out to like a core group of people.
It's like that scene in movies when they detect aliens for the first time. All
Exactly.
the sirens go off. Everyone gets an email. Everyone's like, wait.
Yeah.
Is it?
Yeah. But in this case, so this was still, they were still in the middle of their run phase where they were still testing stuff.
They were like,
but they had so the PA system in the actual control room had not been like configured yet.
So funny.
So it just, the email went out.
Right.
Okay. And the people in the control room had no idea.
That's so
okay.
funny.
So LIGO had just had this $200 million upgrade, right? It was called Advanced LIGO at the time. But they were still getting the bells and whistles of this upgrade together. And there was a likelihood, but people weren't thinking it was going to happen so soon, right? And so the alert goes out, and it's only a handful of data analysts. They see this thing. There's a guy in Germany. There's a guy in the University of Florida. There's obviously guys at Caltech and MIT. They look at this. They're like, yeah, right.
Yeah, right. Yeah.
Yeah, right.
Yeah.
Because it's so beautiful. Oh, no. The signal is like something, you know, like you do simulations and you're like, this is what it should look like. Yeah. And then out comes an email saying, hey, here's what I found. It's like, okay.
It's exactly like
exactly like what you're simulating. So it's like, no, right? And all of the big scientists are like, no, this is too good to be true. The guy at Caltech actually was just like, I don't have time for this. Yeah. He looked at the email. He's like, and then he just went on about, because he's got other stuff to do. It's Advanced LIGO. And you know, his grad students and postdocs are like, did you see the? Did you see it? And he's just like, dude, it's you young people.
Yeah, right.
This is not how it works. Okay,
the world is not idealistic.
Yeah. This is not how it works, and it just wouldn't go away, because usually, you know, they used to have these things called, they would inject noise, blind injections, to see if the system works.
Yes.
So maybe there's a guy who's injecting the fake data in there to see if the email alert works.
Right.
So they call everybody who's in charge of that, and he's like, no, dude, I didn't do that.
Yeah.
They go back into the nitty gritty of the data, of the raw data, and they're like, it's in the raw data.
Yeah.
And they're like, okay, so now they just start getting real paranoid.
Yeah.
They're like, who is doing this?
Yeah, right.
Okay, who is the evil genius that like went into the raw data? And it turns out there's only a handful of people that know the instrument at such a level where they've covered all their tracks. Right? And pretty soon they start thinking like, actually, it can't be a single person. Yeah. Because it happened at both Washington and Louisiana. So it must be a bunch of people. So now it's like there's a giant conspiracy and everyone's looking at each other like, okay, what's going on? Then it turns out, so this happened at 4:50 a.m., right? That night on September 14th, there were two postdocs outside of the Livingston facility that were trying to test the system with local noise. And what they were doing was they got in their car and they were just driving down the arms and just like accelerating and then braking and accelerating and then braking. They were trying to see if this would inject noise into the Livingston facility. Yes. But they had stopped at 4:00 because the guy had to catch a flight at 6 a.m. He's like, I need to get to the airport. Yes. So they call up these postdocs and they're like, what were you doing at 4:50 a.m.? It's like 4:50. Actually, no, I know for a fact that I was driving to the airport. Yes. So it definitely wasn't me. I was nowhere near. And also, like, why would that happen at the Washington facility? But at this point, everyone's like real paranoid, right? So they're trying to be their own worst enemy, trying to see who faked the signal because this signal is just too good. Yes. Right? Like, God isn't this kind. Yes. And at the end of the day, it's like, okay, is this a prank? All of the dudes that could have done this get in a room, and they're just like, all right,
do you do it?
Did you do it?
What about you?
Did you do it? And everyone's like, no, we didn't do it. And it's like, shit.
Silence descends across the room.
It's like, dude, what? Okay, so then you say, okay, so nobody did this. And it's kind of like that Sherlock Holmes quote, right? Where it's like, when you eliminate the impossible, what remains, however improbable, is the truth, right? Is the reality. They're like, dude, this is crazy. So now they start having, they have a blind data augmentation technique where they have a blind team that tries to decipher how likely is this to be chance that the detectors just like randomly, maybe there was an earthquake that was right in the middle that like arrived at the same time or something, you know, or like the detectors themselves like did this like fluctuation randomly. How likely is that? So they start going down this rabbit hole of like, okay, what if, how much of this is a fluke? Because you got to figure out a confidence, right? Remember, the confidence is 5 sigma. So these guys are in charge of that. And they go through, and there's this big unblinding party where they open the box.
It's like
right. They do reveal. All of so what happens? Yeah, what happens is they do all of their analysis without actually looking at the real data.
Got it.
And then they open the box, and then now they take the real data and say, okay, given our analysis, where does given our distribution, where is the real data? Mm-hmm. Okay, they don't even know what the real data is.
Right.
Okay, they've been doing this blind, so they have this unblinding party where they open the box, and everyone knows when this is going to happen. And the party happens, you know, their Zoom meetings are only set up for like 50 people, but like everybody in the collaboration shows up. Right. So it crashes.
Right.
And so then they're scrambling. They're like, okay, we gotta get the Zoom meeting up. Finally get it up. They unblind, and this is well above 5 sigma.
Oh my God.
And everyone is like, that's when the champagne comes out.
Right. Yeah.
That's when they're like, wow, we got him.
We got him.
We got a single gravitational wave that was like so ridiculous, right? Because had those two postdocs been going on their thing for like through 450, we wouldn't have caught this thing that happened. It's such a it's now become like part of like the LIGO lore. Like, and those two postdocs are now like famous because like they decided to like call it early at like 4:00 in the morning. You know, it's so cool to think about that. Like, yeah, like we were listening to, you know, gravitational radiation from billions of light years away from two black holes that merged. And to think about the incredible, like, sensitivity of this instrument. Right. We really haven't gotten into just how incredible this is. I threw around a number like 10 to the minus 20.
Yes.
Right? To give you a sense of how small that is, that's like measuring the distance from the Earth to the sun, and then you add an extra atom to that distance.
To that distance. Yeah.
That's stupid.
Yeah, no, I don't. This is
why Einstein was like, no.
Yeah, no. Because it's so outrageously arrogant for us to think
that we could measure that.
We can measure a disturbance at a degree that is so small and be able to, and make it verifiable.
Yeah. 10 to the minus 19 meters is what we actually did, which 10 to the minus 15 is a proton. So this is 10,000th the distance of the diameter of a proton, the size of a proton.
So we have these 2-3 kilometer tunnels on different sides of the country.
And we're measuring a difference
of a tenth of a proton.
Of 10,000th.
A 10,000th
of a proton. Right? Like the detectors themselves are made out of atoms that are made out of protons, and the protons are like a 10,000th the size of the atom, and now you've got... So it's an incredible achievement, right? And it took 1,000 people,
right?
Experimentalists, theorists, NSF bet big on this. The National Science Foundation really like bet the farm on this thing working, and it worked, right?
And it took decades, and we got them.
And it's a new way to look at the universe, right? Before we were limited to electromagnetic radiation. We had pulled all the stops when it comes to electromagnetic radiation. We had gone all the way from radio, which is long wavelength, all the way from radio to infrared, microwave, infrared, visible, the optical spectrum, ultraviolet, X-ray, gamma ray. We've got gamma ray telescopes that are looking at gamma ray bursts. We've done particle detectors, right? We've had neutrino detectors, cosmic ray detectors, and now
many of which we've talked about previously on this podcast.
And now we were listening to the universe, not just looking at it, right? We were listening to the space-time ripples. And what's crazy is like the ripples that come in, especially for this first discovery, was in the human audible range. And so you could actually just hook up an amplifier and like hear it and hear these black holes coming in. It would be a chirp because the frequency would increase with time. So it would go yip like that, like yip. Because the black holes are coming together, and as they get together, conservation of angular momentum, they're going to speed up.
Yep.
And as they speed up, they're going to release higher frequency gravitational waves. And so the signal that we were seeing, and that's why these guys were like, there's no way this is real.
Right.
Because if you look at the spectrogram, the frequency versus time, you see this characteristic thing. Yeah. It's like exactly like in the simulations. You're just going, come on. There's no way this is real. That's right. And so it took them 5 months from detection to like being confident enough where they were like, all right, let's announce it. Because
as we've talked about, you don't want to put something out that is not prepared for, because everyone's going to come at you with knives out.
Yes, yeah, and especially because in the past, like with Weber and his gravitational wave detector, right? Those were fake. But like this, at this point, it's like they had done all of the work, and the international collaboration had done all the work. They really weren't very confident until they saw the second one.
Oh, okay.
They saw a second one and they're like, oh, okay, this is real. We're like literally listening to the universe. Yeah. Then the Italian collaboration Virgo came online. Virgo is a detector very similar to LIGO. It came online, and the three of them, so the two LIGOs and Virgo, detected a neutron star merger. Mm-hmm. And that was a big deal because now that you've got three, you can actually do triangulation. Right. Okay? With only two detectors, the only signal you really have is the time difference between the arrival here and the arrival here. There. Now, gravitational waves propagate at the speed of light. So, for example, if they both arrived at the same time, then you know that it's on this plane. Yes. Right? And it came from this angle. Yes. But if it arrived here before and then here later, then it came from this angle. Yes. Right? And you get this sort of arc in the sky of where it could have come from. Right. But that's a giant arc. Right. Okay? If you've got three, then you've got three arcs. You've got an arc here, an arc here, and an arc here. Mm-hmm. And wherever those three arcs intersect has got to be the spot that it came from. So then once we had the signal from all three, we could point our telescopes to it and actually see
what is generating
it. And that was crazy because what would end up happening is the gravitational wave comes in first because there's nothing that's impeding gravitational waves. It's just going. Neutrinos actually came in right after because neutrinos also, they don't interact with anything, so they're just coming through. Yes. Light was actually later because light, it was interacting with all the stuff. And then there was a tiny delay. Yes. And so we had just enough time to point our telescopes to this thing and see the neutron stars colliding. And that's where we got our first sense of where these heavy elements, the precious metals, like platinum, gold, these guys, they actually come from these neutron star mergers. More than like supernovae and things like that. It's from these neutron star mergers where we get the gold that's in my wedding ring and things like that, right?
You know what's so
it opened up it's just so cool, dude.
A great story to look back and listen to is our story covering Ice Cube, the neutrino detector in Antarctica, because it kind of explains this neutrino travel time and light travel time and why there's a difference between those two, which the implications of which dovetail with this gravitational wave detection first, neutrino detection right after, light then shortly after. Why is that happening? Go back and listen to our Ice Cube story because we kind of touch on the mechanics of light traveling and neutrinos traveling. Yeah. It's funny because all these things, again, these are just Lego blocks. They're all connected.
Yeah, they're all connected. And now we've got a fourth one, Kagra, in Japan. Yes. We did a story on how all four found the largest black hole merger. Yes. That was another story on the podcast. So now we've got four, so we can triangulate even better. Yes. I think India and Australia are in plans to make their own gravitational wave detectors. So now we're gonna have this entire collaboration, right? And now the trick is, so we've discovered gravitational waves. We can now listen in on gravitational waves. We're getting signals at about the rate of tops 5 a year. Yes. In the volume of the universe that we can listen to. Yes. Right before it gets so small that we can't listen to it. Yes.
So they're at some proximally close location.
Yeah. They're close enough where the gravitational wave hasn't dissipated so much that we're not sensitive. Now, if we make it more sensitive, then we can expand that volume, right? We can actually expand the radius, and the volume goes up by r cubed.
Yes.
So just even 10 to 15% difference in the radius amounts to twice the volume, right? Because you're going to cube that.
Yes.
So now the challenge is, how do we make LIGO better? Where we're not only seeing a larger volume, but the stuff that we're seeing, we're starting to notice all of the overtones and all of the stuff that makes a musical note great, right? If you've heard, like, you know, the note that comes out of your phone when you're trying to tune your guitar, that's a pure note. It's a C or an A, not very interesting, right? But a piano, why is a piano note interesting? It's because there's all of these overtones and nice characteristics from the piano itself that give it that beauty.
Would a way to frame, like, the texture that the
texture, exactly, that's the word I was looking for,
adds to the tone itself,
exactly,
which is a manifestation of its physical construct, like how it physically exists, and on all of that.
Yes, yeah, exactly. Like a guitar string playing the C is different from a piano string playing the C, is different from a violin resonating at C, and it's all because of that texture of the note. And the texture is actually in the form of all of these higher characteristics of that musical note. The overarching note, if you were to do a physics breakdown of it, the overarching note is still going to be that bass C.
Yes.
But all that stuff on top is what gives it the beauty. So the question is, how do we make LIGO see that beauty? That
pure C
in the gravitational wave,
without any of that.
Instead of
texture.
seeing just the C.
Seeing it in its. I got it. Seeing,
you know what I'm saying?
I understand what you're saying.
Instead of seeing just the note, which is what it's good for right now, we're seeing I did a rip, but now there could be stuff on top.
Yes.
That would give us characteristics about the environment that the black holes were in, or the neutron stars were in, right?
Yes.
How long they've been going at it. All of this other stuff, all of the other characteristics. And that's where the recent paper that's out of Caltech and DeepMind comes in.
Got it.
Okay? What they're trying to do is push the sensitivity of LIGO to levels that were unimaginable before. I mean, LIGO itself is unimaginable, right? But now they're taking it a step further with the use of AI. Okay. So why do we need AI, right? LIGO has this problem that's called a wall of noise. Okay, there's a wall of noise right at 10 to 30 hertz. Okay, above 30 hertz, they're pretty good. Okay, but below 30 hertz at these low frequencies, they're having a real issue.
There's too much noise.
There's too much noise. Okay, the noise is coming from seismic effects, like whenever you have a giant earthquake. The earth rings in these low frequencies, and it rings for a while. Okay. On the other, also, the moon tugging on the oceans creates these tides, and the wave action itself is ringing around the earth, creating. So we're pushing that level.
Got it.
And we're trying to get rid of that. Now, what they've tried so far is something called feedback control. And you've actually used feedback control in your own life. You have AirPods, right?
Yes.
The new AirPods, they've got noise canceling. You've probably used noise canceling headphones. The way noise canceling headphones work is they've got a feedback loop that senses low frequency noise, and then that sensor then counteracts that noise and destructively interferes with it to cancel it out. Okay.
Is this creating? It's creating an interference pattern, so it cancels it out.
Yes, exactly. It's creating an interference pattern so that it cancels it out. This works really well on the airplane because the airplane is a low frequency hum, right?
Yep.
That's the ambient noise.
That makes that makes sense because I just was on a flight and I'm like these
are really good. Yeah. The reason why is because the airplane is low frequency, and you can do that with low frequency because with low frequency you have enough time to respond with your control system. Right. The time scale of that vibration is slow enough where you can actually counteract.
Yep.
But now comes a trade-off, right? There's a trade-off because aggressive control at these low frequencies means you're going to introduce noise from the control system itself at higher frequencies.
That makes sense.
right? Now, for noise canceling headphones, it's fine. You might sometimes, if you're really careful, you'll hear a really high pitched tone in your noise canceling.
Yeah.
If you're like really trying to find it, right? But what you're really worried about is the loud low frequency,
right?
And so you're getting rid of that. You're happy on an airplane.
The level of precision we need at headphones is a very different scale than what we're trying to do when we talk about detection at this level.
At this level, at LIGO's level,
right. That
is annoying.
Yeah.
It was not annoying because that's what allowed us the feedback control on the mirrors themselves. You've got these actuators on the mirrors because the mirrors themselves have noise, right?
Yes.
They can be tilted in a certain way. They can be like up and down. If there's like some seismic effect, then the mirrors can wobble, and then the wobble is going to be greater than the 10 to the minus 19 meters that you're trying to do. It's incredibly ridiculous, right? How still you're trying to make these mirrors.
Yes.
Okay. So in order to actually get that, we use these feedback control mechanisms, right? But the feedback control mechanisms inject high frequency noise. The target would be to get rid of that high frequency noise and be limited by only quantum noise by the Heisenberg uncertainty principle.
From that list that we talked about earlier. Yes.
We want to be limited by the universe itself, right? And the laws of quantum mechanics.
Yes.
The quantum mechanics noise comes in two forms. There's shot noise, which is, the laser itself. I mean, at this rate, we're talking about photons hitting the mirror, and the photons are going to hit the mirror at random arrival times.
Yeah.
So that's called shot noise.
because the difference in arrival time is
difference in arrival time in the photon is enough to cause the shot noise. Okay?
God.
That's the level that we're working at with these mirrors.
Yeah.
These mirrors are like kilograms big, and they're worried about like tiny photons hitting it at random times. It's like that's what we're complaining about. The other limit is quantum back action, which is not only is the photon coming at random times, but when it hits and goes back, it's going to transfer momentum.
To the mirror.
And the mirror is going to wobble because the photon has a reaction force.
Right. And because there's multiple points, the reaction force is happening everywhere.
And it's like so that we can't control because the universe is like you're doing too much, buddy.
This is admin privileges only.
Exactly. The fact that you're getting this far already, I'm like, wow. But yeah, let's slow down. But that's where we're trying to get to. Okay.
Makes sense. To having that being the only remaining noise
imagine
in the data set.
It's like okay. And so that's where this scientific AI comes in. Okay. What these guys are trying to do at DeepMind and at Caltech is they're trying to quiet LIGO's control systems using a radically new AI approach. Okay. And this isn't the first time that AI has been sort of used to help scientific collaboration. But most of the time AI has sort of played the role of a data analyst. Right? After the data has been collected. We've talked about the Vera Rubin telescope, right? Once the Vera Rubin takes all of these pictures, AI can go through and sift through and find asteroids that move around or new transient effects from supernovas and things like that. AI can also be used in cosmology for running simulations faster for the universe's evolution and things like that. But this idea of using AI actively in the data acquisition and in the experiment itself is kind of new. It's not without precedent. CERN uses it at the Large Hadron Collider. They actually use AI algorithms and machine learning systems to actually trigger whether to keep a certain particle scattered data or whether to discard it. So there's a machine learning algorithm that basically makes this split-second decision on whether a particle collision and the shower that came afterwards is interesting or whether it's something that you don't want to save. Because the amount of the particle collisions that are happening are astronomical. I mean, even though CERN's data storage capabilities are insane, it's not going to be able to save everything, right? So you need some way to sift through that, and machine learning is doing that. It's also accelerating simulations on these particle systems. But this approach from LIGO is another thing in that vein of using AI actively in the experiment itself. So what they figured was, okay, we're trying to keep the mirror as still as possible. Okay? Why don't we use a reinforcement learning agent to train and devise its own strategy on how to keep the mirror stationary?
And it's great that we just did an episode on reinforcement learning because it goes very deep into the structure of why this was in our DeepSeek coverage. DeepSeek just did these 2 papers about how they went from human feedback
to just pure reinforcement learning.
And so the point about pure reinforcement learning here is that you as the human who is designing the AI system are not giving it feedback about whether the answer that it's going down is correct or incorrect, which enables, I think the point here is like novel ideas about how to solve the problem that's not limited by our perspective or our perception.
Yeah, exactly. In this case, the reinforcement learning agent is going to just try all these different strategies, see what worked, and then go down that path and make that strategy better.
Yes.
And that's exactly what they did. They created a reinforcement learning agent. They gave it an environment, which is this highly accurate computer simulation of LIGO. I mean, they can't give it LIGO, right? LIGO is busy trying to listen, right? So they made a computer simulation of LIGO, and that's the environment that this agent is now playing around with. The current mirror was the state, like whatever the mirror was, and then the action it could take was, moving it with all the actuators. And it could play around and figure out how to keep this mirror as still as possible. And you can inject noise into it and see how it would do.
And you can do it hundreds and thousands, millions of times. And different parameters.
Different parameters, and you can see, and you can give it a reward every time it does a good job, and you can penalize it every time it does a bad job. In this case, the process of actually rewarding it was actually kind of cool, because you can't just be like, keep it still. That's a little too much freedom. So what they did was they created 3 distinct bands in the frequency space. They called this approach the DLS approach, which is deep loop shaping. Loop shaping meaning this kind of control paradigm where you're worrying about the frequency response of your system, and deep from deep learning. Okay, so deep loop shaping. What they did was they got that frequency band of all of the noise, and they split it up into 3 different categories. So there's a low pass filter for stuff that's below 3 hertz. 3 hertz meaning 3 cycles per second. And that's where all of the seismic disturbances, your sort of the tides and all of this stuff comes at that low frequency.
For people who play, like who work in music, this is like all the bass.
The bass, yes.
Yeah, so
this is the bass,
right? Okay.
Yeah, and with that bass stuff, it basically said you're gonna get aggressive stabilization. We want to teach you aggressive stabilization. You get a high reward if you eliminate the bass noise. Okay, great. Then there's the bandpass filter of 8 to 30 hertz. That's the part that we're trying to really optimize. Okay. That's where the control noise comes in from these guys. And so what they gave was a penalty, a negative reward, if it got any noise
in that 8 to 30
hertz. Okay. The low part was just reward, positive. But this has a negative reward. Okay, it's like penalizing heavily, and the high pass filter also penalizing. Okay, but different weights. And then the crucial thing what they did was they multiplied the rewards at the end to give a final reward instead of adding. A lot of reinforcement learning techniques have added with additive reward. Nowadays, people are slowly foraying into this idea of multiplicative. The problem with multiplication of reward is it can easily blow up. And like be very dangerous. But there's come mitigation strategies against that. And so now with multiplicative reward, you force the agent to perform well on all 3 tasks, not just one.
Right, because you can have one in the summation model. You can have one that's super, super high that kind of drowns out.
And it's just like zero noise in the bass, but then you're just like completely wrecked in the other ones.
That's actually interesting. It through the math, it sort of forces equal distribution of optimization.
Exactly. Yeah, that's exactly right.
Interesting.
And so they tested it on this digital twin that they had made of LIGO, and it worked really well. And they're like, okay, this is pretty cool. They injected noise, and it was still able to do it. And then for 1 hour, they were given time.
Instrument. LIGO's real busy. You gotta check the schedule. I think we can get you 1 hour.
They got 1 hour on LIGO, and they installed this device on LIGO, and it was a great success. The AI controller stably managed these mirrors for an hour, and the amount of noise on the actual thing,
the physical
Livingston Observatory. They got the controls for the actuators.
Yes.
They attached it to this agent. Yes. They're like,
that was the driver of the bus.
Mm-hmm. And now you take the wheel. Let's see what you do. And for over an hour in real world conditions.
Yes.
And the noise was like shot.
Like it
insane. Like an insane amount. Right? And it's like, oh.
Yeah, like
this is the future.
This is the future.
Yeah.
There's so many. I could talk about this
forever. They were getting down to quantum level, dude. They got down to that quantum limit. They were saying the noise level was well below the design goal, being 10 times quieter than the quantum back action limit.
Holy moly!
And so now that they did it on Livingston, now they're going to make it even better. Put it on both LIGOs. They're going to give it to Virgo, put it on theirs. Give it to Cagra, put it on theirs. And then now we're going to have 4 gravitational observatories that are limited by quantum noise.
It's so incredible. Like, I think
insane.
The efficacy and impact. I mean, there's so many levels to this. One is our ability to create a digital twin to such levels of fidelity that it translates from the simulated environment to the real world environment
so well.
Like that in and of itself.
Yeah, that itself is great.
Thinking about the reward model and using reinforcement learning and finding a way to get that reinforcement learning really tight, such that the optimization that it ended up with again gets to that degree. And it's basically, we're just going to do a software patch. I know that's not literally the translation, but
kind of
like it's the existing hardware does not change at all. And every one of these 4 detectors globally is just going to get this 10x noise reduction optimization benefit, just at a relatively snap of a finger, given the time scale it took to build LIGO.
And to be fair, the noise reduction is more than 10x.
It's okay. Wow.
Right?
Okay.
It's like from before to now, the noise reduction is like 10 to the 3.
Oh,
it's just that now we're below the quantum noise by 10x.
Got it.
So now the limiting is the quantum noise. And that I don't know what to do with that, right?
Bro, this is so insane.
It's insane. And this has actionable consequences on what LIGO can see. For one, it's more sensitive, so it's got a larger volume of the universe.
Right.
But the other, it's now sensitive to a new frequency band, this 10 to 30 hertz, right? Which was not accessible to us before.
Right.
And this is exactly where you have intermediate black holes. Intermediate mass black holes. And this is going to help us solve a huge
supermassive. So it's like
it's
like smaller
exactly
in size.
Smaller in size from supermassive, but larger in size from stellar mass.
Got it.
There's been this contention in the black hole physics community about where the hell are the rest of the black holes. We see a bunch of stellar mass black holes, right, with LIGO and things like that. We obviously see supermassive black holes at the center of galaxies, but the black hole mass gap is what it's called. This gap between supermassive and stellar mass, this intermediate mass black holes, where are they? Well, now LIGO is going to be sensitive to those intermediate mass black hole mergers, because those would happen slower than the stellar mass. The stellar mass, they can get closer together, and if you get closer together, you speed up, right? Neutron stars as well. The closer you get, the more you speed up. So with the neutron stars, you can actually start observing them earlier in their decay cycle, right? Where before you had to sort of wait till they got really close to create these big, fast gravitational waves. Now you can spy on them from the very beginning and see them speed up and get closer and closer together.
The idea, and just to make sure I'm kind of understanding, the idea is part of the spinning and the closeness is what dictates the size of the gravitational wave that's being sent. And this is where we talked about they have to be really, really big when we started for us to see them, because we couldn't detect at this range. By having this range now accessible to us, we can detect fainter gravitational waves, which one of the sources being these intermediate black hole
and the other one being the neutron star mergers earlier
right? In its
so now, like, you can imagine you can have a early warning system,
right,
that something's going to happen, and then, but minutes in advance, not like fraction of a second,
right?
Because the gravitational wave itself lasts, the ones that we've seen last like fractions of a second,
right?
Because that's when they get close enough to actually get big enough. The waves get big enough for us to see.
Yes.
But like now we can have a minutes long advanced.
Yes.
Where now,
yes,
even the James Webb with minutes, James Webb could drop what it's doing and like point. And point, and we could see it at the moment.
And so this is a combination of being able to hear the universe and see the universe, and this sort of new level of accessibility allows us to combine both of these tool sets in combination to be able to now not only hear it, have a window of time that's long enough that any number of different Earth-based or space-based detection platforms that are looking at infrared or optical could look in the direction of the source, because we have 4 locations. So we can triangulate a smaller region of space in the sky to point, and now we can get this multispectral view of these like crazy events. Oh my goodness.
It's like we really are living in a golden age of time domain astronomy, right? We had a golden age of astronomy in general, but it's like we were looking at still pictures, right? And now the universe is dynamic, and we have access to that extra dimension,
which is time passing, and us then seeing the transition of these objects over time with really, really high fidelity.
We have early warning systems now. We got the Vera Rubin that's going to find random stuff. And this is another, now that we have this 10 to 30 hertz band that we're sensitive to, we got that unknown unknowns coming back again, right?
This is, I think, what's so interesting. This time domain astronomy point is, it's like we're turning on the light for the first time. We've sort of been like having candlelight in this.
We've been doing flash photography.
Right. In this like small window. And so not only do we have a larger window, we also now have this ability to see things in time, which again means our ability to understand what's actually happening in the universe around us is like right now, today. Like not 20 years ago, not 50 years into the future. We talk about Vera Rubin. It's going to be putting out data every 3 days globally in real time. That's going to see things we've literally never seen before. And lots of it. Like lots of it. This is, I love these retrospectives because science is a story. It's a human story. It transcends generations. We're building on the work, the blood, sweat, and tears of those before us. And we are expanding the aperture by which we, again, can just understand so many pieces. And people always talk about AI in this like, in just purely generative LLM, ChatGPT universe of like, these LLMs aren't that great. It's just this stochastic parrot that repeats back what it's already heard before.
No.
Like this, like one of the reasons, like this,
it's doing things that we really wanted it to do, and is doing it way better than we could do it.
Right. Or that we necessarily even thought it could do at this stage in its development cycle. And I think it's why it's so important to talk about these AI stories in the context of the experimental design, of the historical storyline of these like instruments, right? Because at the end of the day, science is so much about instruments. And when we talk about experimental stuff, and this is why we spend hundreds of millions of dollars on this stuff.